Today we're going to continue talking about our predominant species and our principal species in solution, but this time quantifying a little bit using a fractional composition equation. And we're going to focus in a minute on a molecule that's polyprotic called EDTA. But first, we need to define a few things. The fraction of molecules in a given form we're going to call alpha. And the fractional composition is dependent on pH and pKa. So the polyprotic species that we're going to use is EDTA, ethylene diamine tetraacetic acid. Ethylene diamine tetraacetic acid, when it's fully deprotonated, can bind onto metals, and it's really useful for removing things that are toxic from solution. And it's a great model set because it has 6 protons that can be removed, so it has 6 acidic protons, and is a great model for fractional composition and for determining the dominant species in solution. So I've identified on the molecule here the 6 acidic protons. Those include 2 hydrogens that we have to add to the nitrogens, giving each of these nitrogens a resulting positive formal charge. The fully protonated species is abbreviated as H6Y2+, because of these 6 acidic protons that are on the molecule with a total of a 2+ charge, where Y is equal to EDTA. So the hexaprotic species H6Y2+ is in equilibrium with Y4-, the fully deprotonated species, and giving up a total of 6 protons. This is the overall equation, but we can break it down to individual steps, where at low pH we have H6Y2+. We then deprotonated by Ka1 to make H5Y+, which gets deprotonated to form H4Y, and then H3Y-, and then H2Y2-, and then HY3-, and then finally at really high pH, Y4-, the completely deprotonated species. The fractional composition of the fully deprotonated EDTA is given using this symbol here, alpha Y4-, and that is equal to the concentration of our fully deprotonated species, Y4-, divided by the sum of all of the species in solution, which is all of the forms of EDTA, which is sometimes why this expression gets simplified down to being the concentration of Y4- divided by the concentration of all of the EDTA. The form of the EDTA that we will focus on is Y4-, because this is the form that binds to metals. Once all of these have been deprotonated, the metal is wrapped around by the ligand. When the ligand, the EDTA, binds to the metal, this results in a new K value for us, called a formation constant, K sub F, and that's usually very, very large. So K is associated with the following reaction, where you have M of a certain oxidation state reacting with a ligand, which should have a minus charge on it, in equilibrium with Ml, the complex, because once the ligand, a thing that binds to the metal, it forms a complex. The result is a expression, Kf, which is equal to the concentration of the complex, Ml, divided by the concentration of the ion, M, times the concentration of the ligand, L. For EDTA, that would look something like this, where we have a metal of a certain oxidation state reacts with EDTA 4- to form a complex that is that metal's oxidation state -4, to account for the 4- charge that EDTA brings along. Kf associated with this is again equal to products over reactants. So let's use a simple example to show how these are used. So example 3, what is the formation constant expression for EDTA bound to metal 3, to metal iron in the +3 oxidation state? So iron 3 reacts with EDTA, Y4- to form iron EDTA with a -1 charge. The Kf value that's associated with this reaction is again products over reactants, so we get iron EDTA complex with a -1 charge in the numerator, and the iron ion multiplied by the EDTA ion in the denominator. Now, here's something that's a little bit different than what we've seen before. Formation constant expressions for metals binding EDTA have been determined for many metals of different oxidation states. Since only one form of EDTA, Y4-, will bind to the metal as a hexadentate ligand, the true Kf value is dependent on alpha Y4-. This is called the conditional formation constant Kf prime. Now this is analogous to a certain degree to activity, where we had a certain equilibrium constant that was affected by a gamma value. This situation, we have an equilibrium constant Kf that is being modified by our alpha. So what ends up happening is the higher the pH, the more of EDTA 4- you have, the more EDTA has been fully deprotonated. At a lower pH, you have very little EDTA 4- in solution. So what is the Kf prime for EDTA plus manganese 2 plus at a pH of 3? To answer this equation, or question rather, we need to refer to tables 12.1 and 12.2. So first, we need to figure out what pH that we are at. EDTA has been studied to a great degree, and we know very precise alpha values at different pHs for EDTA. In this situation, we're dealing with a pH that's equal to 3. For a pH of 3, we have a fractional composition value, an alpha, that's equal to 2.1 times 10 to the negative 11 for EDTA. So that's the value of alpha that we're going to use. The metal that we're using is manganese in the +2 oxidation state. Over here, we have manganese in the +2 oxidation state, and we have a value of 13.89. It's very important to realize that that 13.89 value is presented in the form of the log of Kf. So in order to get to the Kf, we need to do 10 raised to that value. So we can summarize the information here. At a pH of 3, we have an alpha value that's equal to 2.1 times 10 to the negative 11. And for a manganese 2 plus, we have a log of Kf that's equal to 13.89. 10 raised to that value ends up giving us a Kf that's equal to 7.8 times 10 to the 13th. When we bring these values together, we can solve for our conditional formation constant. So Kf prime is equal to alpha times Kf. Kf prime is equal to 2.1 times 10 to the negative 11 times 7.8 times 10 to the negative 13. So Kf prime is equal to 1,638, or 1.64 times 10 to the third. This is a large number. This is one of our first equilibrium constants that's not a very negative exponent. So we have a positive exponent. So, as a conceptual question, would Kf prime be higher or lower at a higher pH? Well, as we increase the pH, we are increasing the basicity. And when we increase the basicity, we end up making more of the form of interest, right? So when EDTA is completely deprotonated and we have the Y4-, that's the one that can bind metal. So if we're at a low pH and we have the completely acidic species, we're not going to have very much EDTA 4-. But if we're at a very high pH, we have mostly our fully deprotonated form. So this is actually one of those first examples, I believe, where we've seen that the concentration of something actually changes the constant itself. So as we increase the pH, we increase the basicity, and we would increase the amount of EDTA that we have, and that's exactly what we see happen. pH, when it is 0, very, very acidic, we have very little EDTA in solution. We have alpha value, a fractional composition that's equal to 10 to the negative 23rd, very small. But once we go up in pH to 13, 14, we have only EDTA Y4- in solution, so we have an alpha value that's equal to 1 when it is 100% the fully deprotonated form. In example 6, we're going to be calculating the concentration of the metal ion in a solution where we start with the complex, and we have 0.050 of chromium EDTA at a pH of 10. So we need to first identify what our equilibrium expression is, and then we can move on from there. So our Kf prime value is going to be equal to alpha of Y4- times Kf. Now, we need to use those tables in the back to figure out what those two values are. So first, at a pH of 10, which is given in the problem, our alpha value is 0.30. So we can record that here. Our Kf is going to be for chromium 3+. Chromium 3+ is found here in table 12.2, and that's equal to a log of Kf that's equal to 23.4, shown here. So our Kf is going to be equal to 10 raised to that value, 23.4, which is 2.51 times 10 to the 23rd. So now we can solve for Kf prime, which is going to be equal to 0.30 times 2.51 times 10 to the 23rd, which is 7.54 times 10 to the 22nd. That will be equal to our products over reactants. The chromium EDTA complex divided by the chromium ion concentration times the EDTA concentration. Now, it's important to realize what is happening in solution. So an abbreviated ice table is shown here, where we have chromium reacting with EDTA with our Kf prime value, equilibrium constant, to reach our chromium EDTA complex. We are starting with the chromium EDTA complex. That's the thing that's dropped into solution. So we have 0 of each of these initially. And the shift is actually happening in the reverse direction towards the reactant. Here we are starting with the chromium EDTA complex. We have 0 concentration of EDTA and chromium in solution, and so the EDTA goes down in concentration while each of these goes up in concentration. So at equilibrium, we have 0.050 minus x, and we have x and x for our reactants, because we have a shift towards the reactants. This is, again, a little bit different from things that we've seen before, but it follows the same principles. We're starting with a solution here that has a concentration, and we have no concentration here, so Le Chatelier's principle is going to shift it towards the reactants. So our expression for Kf, we can bring in values now. So Kf prime is equal to 7.54 times 10 to the 22nd, which we calculated, and that's going to be equal to 0.050 minus x divided by x squared once we are at equilibrium. We can then ignore this x as we have before and rearrange, and we get that 7.54 times 10 to the 22nd is times x squared is going to be equal to 0.050, and we solve for x, which is 8.14 times 10 to the negative 13, and turns out that that is the chromium 3 plus solution, the chromium 3 plus concentration, which is equal to 8.14 times 10 to the negative 13 molar. Moving on to our next set, in our example 7, which is a continuation of EDTA, we're now going to figure out what is the cobalt concentration, the cobalt concentration in solution and the EDTA concentration in solution after two mixtures have been mixed together. So this is a situation where we have initial cobalt and initial EDTA, and we don't have any of the complex. So what we're going to need first are a few values. First, we're going to need our alpha value at this certain pH. It's a pH of 10, which again gives us an alpha value that's equal to 0.30. We're now going to move on and look at another example of EDTA, except this time it's when we have an initial concentration of a metal and the EDTA, and we have none of the complex. So we need to see what happens when these two things are reacted. So we have a situation where a solution of cobalt 2 plus, that is 0.030 molar, and we have a volume of 50 milliliters, is mixed with 50 milliliters of a 0.050 molar EDTA solution at a pH of 10. So before we get started, we can record a few values. Our alpha value is at a pH of 10, which is again equal to 0.30. The metal that we're interested in is cobalt at the +2 oxidation state, which has a log of Kf that's equal to 16.45. When our log of Kf is equal to 16.45, our Kf is equal to 2.82 times 10 to the 16, because we do 10 raised to that value. Our Kf prime expression is going to be equal to alpha times Kf, which is equal to 0.30 times 2.82 times 10 to the 16th, which ends up being 8.46 times 10 to the 50th. Now, in order to see how these are going to react, we need the moles of each component. So cobalt 2 plus reacts with EDTA 4 minus to form cobalt EDTA 2 minus. So initially we have cobalt moles that are equal to 0.030 moles per liter multiplied by our initial volume, which is 0.050 liters, to find out that we have 0.0015 moles of cobalt 2 plus. So that's our initial moles of our metal ion. Our initial moles of our EDTA ion is equal to 0.050 moles per liter times 0.050 liters, which is equal to 0.0025 moles of our fully deprotonated EDTA. When we consider how they are going to react, we can start initially with our moles. So we have 0.0015 moles of cobalt. We have 0.0025 moles of EDTA. Now, our change is going to be a little different than what we've seen before. Since Kf is very, very, very large, these are large positive exponents, we need to assume that everything that can react will react. In that situation here, we are limited by our amount of cobalt moles, so all of our cobalt moles react. We have more of EDTA because that's in excess. So our change is we subtract 0.0015 of each, and we produce 0.0015 moles of our complex. So at equilibrium, we have no more cobalt moles remaining. We have 0.001 moles remaining of EDTA, and we have formed 0.0015 moles of our cobalt EDTA product. We assume that all of the limiting reagent reacts because Kf is very large. And we'll pick up there next class.